All right, well, we're going to get started. We're going to take just a few notes and then do a kind of rush a little bit through an example problem because I want to have some time at the end to watch a few videos. So we're going to start just taking like normal notes. I apologize for my voice. Baseball practice with my second grader apparently did not do me any help. We have another practice tonight, so I'm going to be like totally toast. Such is life. So before we start though, I want to just briefly touch on, so I sent an email out yesterday about the design project. So there are a few new example problems that are up on Moodle. Some example problems that I go through, like I posted some videos, so if you want to like hear a video walkthrough, that's available, or just like the written solution. All of that is posted depending on how you want to look at that. There's also a document that I put on Moodle that's hopefully you find useful. It's kind of like this is where I expect you to be, and maybe this is a good framework for you to think about like what should we do next in terms of like where you should be with your partner, what you should be thinking about, kind of where you should be in the process. So the report is coming up, I mean, in a little bit, but it's going to come fast. So I want to make sure that you're still, tied in with that. It's not going to be an assignment that's due, but this is, I think, I kind of put what I would expect is by Monday, you've kind of gone through some of this and you know basically what you're doing. You have some of the aspects divided up and you kind of know what each person is going to be working on. Some general ideas for the design project problem. Something that I see a lot when you're making these computer solutions, it's easy to screw up like a sign or something like that and get something that's giving you what looks like a right answer, but turns out to be garbage. So just make sure after you kind of get the basics set up, right, your first goal is to just get something that models a system. It doesn't need to be an optimized system. It needs to be like, this is a working system. And then you can go through and just do like some basic sanity checks, like what should happen if we raise the height? Well, we should get more power. So does it respond in ways that make sense? If you raise the height and your power goes down, okay, let's find where we messed up. If you may use bigger pipes and your power goes down, you go, well, maybe we did something wrong. So just like do some kind of sanity checks to make sure things are working how they should be working before you try to go and use that model to then do any optimization or any experiments kind of on the working of your system. So hopefully you continue to make progress on that. I think there are a lot of resources there. The book has a lot of stuff as well. Similar to this, there's a lot of example problems in chapter 8. So in addition to the ones that I have, if you are kind of looking through how to think about these problems. Right, what we're doing in a lot of this is looking at, it's a mix of stuff that we did in thermo. All of that stuff doesn't like go out the window. We're just looking at it kind of more in depth in certain parts. So when you're thinking about like, how do we deal with efficiency and all of those things, it's the same as what we did in thermal. We're just looking more in depth at the fluid flow parts of it and like fluid friction and things like that we kind of glossed over. I don't know, but maybe that's helpful to think back, like how would we have thought about this in thermal class? What we're going to look at today, like I said, we'll kind of briefly touch on how we can calculate head loss in different types of flow. So what we looked at last time was for we called major losses, or HL. If we have a laminar flow, pipe. The head loss was equal to 64 over the Reynolds number, the length of that pipe over the diameter, times velocity squared over 2. We were actually able to figure out this from first principles, from the Navier-Stokes equation. We can figure out a similar model for turbulent flow. We expect it to be similar because they're broadly similar, but also a little bit different. So for turbulent flow, this is kind of where we ended last time. We're going to, instead of 64 over the Reynolds number, it's going to be something, a number, a constant, times L over D, B squared over 2. And this, as the friction factor is dependent on a Reynolds number and what we call E over D, which is the relative roughness of the pipe. So surface roughness of the pipe is going to come into play in turbulent flow. So, right, one of the challenges of these problems is Reynolds number depends on velocity, but velocity is going to depend on how much friction there is. So a lot of these things we're going to have to solve iteratively. And we'll see that in a second when we do an example problem. We can find graphically figure 8.13. I'll show you what that looks like in a second. Or by equations, which are just fits to experimental data. So here's one fit. This is a relatively famous one, relatively useful. 2.0, negative 2.0 times the log of E over D divided by 3.7 plus 2.51 over the Reynolds number times the square root of F. So you can see friction factor, you can see that it depends on E over D and Reynolds number on the right-hand side. But this equation is, while it's useful, it's also an implicit equation, which means it's got F on both sides. So you can't just solve it easily. You have to solve it. You have to guess a value of F and then use that on the right-hand side and kind of see what it gives you on the left-hand side and see if those match. So you're going to have to solve this iteratively to be able to get it to work. Okay. Let me pull up that chart. So this is the Moody chart. I think, did I show this briefly last time? So what you're going to do is find Reynolds number. Like, where are you here along the bottom? Then you're going to find the relative roughness of your pipe. So that's going to tell you which of these lines on the right to follow. And you're going to find, okay, say I'm down here. You're going to trace that line and this line and say, okay, that's where those meet. And then I'm going to go over here to the right side, and that's F. So you have to use both Reynolds number and the relative roughness. The relative roughness, again, these are data that you can find. Sometimes if you're like purchasing something from a manufacturer, they might have relative roughness for that thing. Otherwise, kind of common values for different materials. The book has some. So you'll notice like pipes generally are fairly smooth, because if they're not, then there's a whole lot of friction. But different materials can actually have fairly different roughnesses, as you guys just know from common sense. One of the things when you're calculating the relative roughness, you have to make sure the units match. So you can see here just some values in both millimeters and feet. So if you're going to calculate it, just make sure that you're using millimeters for the roughness and millimeters for the diameter, or feet for the roughness and feet for the diameter, just so that those units match up and you get a unitless relative roughness. Okay, there's also, there's that equation, the implicit equation for F that I wrote. There is also, our book has an explicit equation for F, like a normal one, like an F equals equation, which describes behavior for smooth pipes. So you can see basically all of these, the relative roughness kind of all end up falling on this line here if they're really smooth. And really smooth is kind of dependent on Reynolds number, like what really smooth actually is. But if your pipe is really smooth, if it has a very low relative roughness, you might fall along this line, and then it's actually fairly straightforward to calculate. If you have, so this is for, give me my thing back. These models are for major losses, just flow down a straight section of pipe. We would expect minor losses like flow around a corner, things like that, to be dependent on the same types of things, like Reynolds number and what the thing is, like is it an elbow or whatever, and diameter, things like that. Minor losses, the general model that we're going to use is, again, it's really similar. It's going to be K times V squared over 2, where K is the loss coefficient, which is a value determined from experiment. So you can predict it if you do simulations for something, but generally it's fairly easy to measure. So if you looked at like buying a valve from some supplier, you can actually usually find on the supplier's website, like what's the loss coefficient for this valve when it's all the way open. So this is often something that like kind of is one of the specs for that particular thing. Our book has a lot of values in it as well. There are whole handbooks just of like loss coefficients for different types of things. Our book has a lot of data that we use for this class. So for example, you can see, okay, so these are different types of entrances. So if you have like a pipe sticking out into your tank, your loss coefficient might be somewhere 0.5 to 1. If you have just a square-edged entrance like this, maybe it's 0.5. Again, these are kind of generic ballpark numbers, but they can give you a good idea as a starting place. If you have a rounded entrance, well, then your loss coefficient is going to depend on kind of the degree of curvature of that entrance. So then you may be able to get as low as 0.04. You might have less friction losses if you have kind of a gradual entrance than if you have just an entrance like this one here, just a straight wall with a pipe coming out of it. There are tables, again, our book has just like a small fraction. There are whole handbooks of like a whole book just of this kind of stuff. But it has enough for us to use for our purposes. Right, different kinds of elbows, different 90-degree elbows. What do the joints look like? What is it? You can see a little bit of the variation that there can be even in like a single type of thing. You can see like here, all different kinds of valves. When they're wide open, it's going to be like, again, depending on the design of the valve, it could be a very different thing. How much friction actually is occurring in that valve. Same thing with like an expansion or contraction. You might have like tables of loss coefficients, or you may have, something like this that's kind of like a maybe an equation or a chart kind of correlation. So there are lots of different ways to present this data. It's going to be experimental data that you kind of have to say, what am I getting what is the thing that I'm looking for? And then you have to go and figure out, okay, how can I find the value for K? It's generally fairly easy. There's some way to look it up or to calculate it depending on what specific thing you're going to be looking at. Okay, so if you want to flip now to the one-page handout, what we're going to do is a relatively quick example of how we would find flow rate for a fire protection system. So I'll flip over to it too. So this is the example that you guys have. Our book also goes through, this is example 8.7 in our book. So if you want to go and back and look at how the book does it, that may help you as well if you get kind of lost for some reason. What we have is a water tower that's 80 feet tall, and we're going to use the potential energy from that water tower to, we're going to use that pressure to push water out the end of our fire hose, and we want to figure out how much that is. So when we have pipe flow problems, the big general equation that you're going to start with is the head loss equation. So you're going to write the total head loss is equal to P1 over rho plus alpha, the total energy at control surface 1, right? The total mechanical energy minus the total mechanical energy at control surface 2. So but pressure, kinetic, and potential. Okay. Then you want to go through and actually look at your specific problem and say, which types of mechanical energy do we have at which locations? So we can simplify this a little bit. Our first simplification, we know, okay, so our two control surfaces are, right, the top surface there, that's 1, and the outlet there, that's 2. So we're shooting to atmospheric pressure, so at the outlet, that's going to be atmospheric pressure. And like in the water tower itself, we're also going to be at atmospheric pressure. So the first simplification, P1 equals P2 equals atmospheric. So we can take and cross out both of those because they're zero gauge pressure. And they happen to be identical. The other simplification that we can do for this problem is, again, we're looking at like the water at control surface 1. What kind of energy does it have? Well, it has potential energy because it's high up in the air. It also is going to have some kinetic energy as it's like, as that level is dropping, but it's moving slowly, but very slowly. So we can say it's practically not moving. So the average velocity at 1 is about equal to 0. It's not going to be exactly 0 because that level is dropping, but it's slow. So maybe it's dropping, I don't know, it depends on how big the water tower is, but it's maybe dropping like inches per minute. So that's not a lot of kinetic energy. The other simplification that we're going to make is we're going to assume our velocities are probably pretty big because this is like a fire hose. So we're probably turbulent. So let's assume turbulent flow with alpha. So this would be alpha 2 equals 1. And we can always go back and double check that to make sure that that's actually correct. And if it's not, then okay, we can go back and fix it. But we'll just kind of guess that it's probably turbulent flow, right? Like if you take even your faucet at home and open it all the way, you have turbulent flow. So that's a good assumption that we're probably going to be turbulent flow. Yeah, Nick.
Could you explain why it's like the tank is atmosphere?
So it's a water tower, which is probably like not pressurized in the top. So there's probably like a vent that's open just to the air. So that's, yeah, I guess nothing too specific, just kind of thinking about what's happening with that surface. So if you had something that was specifically pressurizing that, if you don't have it open to the atmosphere, right, as the water level drops, you'll actually form a vacuum there, which will decrease your flow rate. So it's easiest to just like have a vent there so that as the water level drops, air is going to come in and refill it. So it'll probably be atmospheric. Okay, so this is going to simplify. That term gets canceled out because of our second bullet point. And our simplified, our head loss equation, the total head loss equals G Z1 minus Z2 minus alpha 2 velocity 2 squared over 2. Okay, our minor losses sum of all of the different minor losses. So if you have like minor losses from this thing and this thing and this thing and this thing, you just add them all up. We are told, let's see. So here it says the pipe contains 1 gate valve. Other minor losses may be neglected. So we have to go and look up what our minor loss coefficient is going to be. Let's go and look at this table. We have 1 gate valve. So when our gate valve is wide open, our minor loss coefficient is 0.2. Okay, so this equals 0.2 V2 squared over 2. And that's because that's the velocity going through the gate valve, is the velocity going out. Major losses, we assumed turbulent flow. So our major losses are going to be like this. We need to figure out what F is, and we need to figure out so here, L over D, that's the total length of like straight pipe in the system. So if you think about it, we have to go about 80 feet, maybe not exactly, but about 80 feet, and then 600 feet that way. So this is about equal to 80 feet plus 600 feet divided by 4 inches. But I'm going to divide that by 12 inches per foot to get the units to work out. So the length over the diameter is, I believe it's 2040. Okay. Then we have to find, if you flip it over to the back, we'll start on the back. So find F. It's a function of the relative roughness and the Reynolds number. So we'll look up what the relative roughness of cast iron, which is our pipe material. Again, if we look that up, so there's cast iron. So our relative roughness in feet is 0.00085. 0.00085 feet. This is from. So a lot of these problems, you have to go back and look up a lot of data in tables to figure out what is for this particular thing. So if we look back at our problem statement, we're told that this is made of cast iron and it's about 20 years old. So I'm just going to make this part up, but we'll say it's probably not the same as what brand new pipe is. And it's probably got some gunk in it. So let's say that the roughness of our old pipe is about 3 times what it would be for a new pipe. I don't know that that's true. I'm making it up. But typically, this is what's going to happen is things, and we'll be able to, once you get a solution, you can check like how much does roughness actually contribute to it. So this would give us a relative roughness of 0.00255 feet. And the roughness over the diameter is 0.0077. So the Reynolds number is equal to rho v d over mu. We don't know the velocity. So that's a problem. Like, to figure out the friction factor, we need to know the velocity, but to figure out the velocity, we need to know the friction factor. So you typically are going to have to solve these problems in some way iteratively. You're going to have to use a computer to be able to, like, let's guess what the velocity is. Maybe it's, I don't know, 2 feet per second, and make up a number to get an answer, and then go back and check, use a computer to be able to run kind of a guess and check like this. If for this problem, if the Reynolds number is greater than about 10 to the 5, then F is about equal to 0.035. I'll show you a second what why that is. Let's look at our chart. Oh, this one. So we are 0.077, so we're pretty much on this line. So you can see that line is really flat as long as we're above about 10 to the 5. If we're below 10 to the 5, then it starts to curve up. But as long as, if Reynolds number is above 10 to the 5, we're going to be about there, 0.035. So that's a pretty good initial guess. And if we're wrong, then we'll go back and fix it afterward. So I'll just write a note. Okay, then what we would end up getting is, okay, we would have 0.0035 times 2040 v squared over 2. That's our major losses. We would add to that our minor losses, 0.5 v squared over 2. That would be equal to G Z 1 minus, sorry, you're right. So it would be 32 feet per second squared times 80 feet minus 1.0 v squared over 2. So that would be G Z1 minus Z2, our height difference of 80 feet, minus alpha V2 over 2. Okay, and then we would go through and solve that for velocity, and then we could solve that for flow rate. So this would give us a velocity of about 7.8 feet per second. Yeah, Nolan.
Should that allow the velocity or the VT
These these all should be squared. So that should be squared, squared, and squared. Here? No, that's that. No, yes. Yes. So all of those are velocity squared. So I'll put up on Moodle, there's like a little spreadsheet that you can play around with some of these numbers. Okay, so, yeah, Graham.
We don't incorporate it.
So, okay, then you could go, if you wanted to add more minor losses, this problem we were specifically told not to, but if you wanted to be like a better solution, you would just keep adding, okay, this minor loss and this minor loss and this minor loss, and you would get just more terms on the right, on the left-hand side. Like 0.5 or point, this is, I guess, 0.2, isn't it? 0.2 is the minor loss coefficient. So you'd have to figure out the minor loss coefficient for each of those different things that you have. But all of it is going to be additive. So that's one of the nice things about head loss is it's an additive thing. So you have to figure out, okay, what's the head loss for this little part? What's the head loss for this part? What's the head loss for this part? And you can figure out and just add those all together. Because it's like, it's friction, right? It's going to be additive. It's how much did you lose? Okay, so if you can flip over to this guy and we'll watch a few brief videos and we'll pick this up again next time because we don't have nearly enough time for it today. But while you're flipping to this, I'm going to flip which screen is presenting and stuff. While you're doing that, see if you can't draw part A and C for number 1. So don't worry about part B, but see if you can't figure out A and C for this first valve. Basically, you're going to be drawing like the pressure position. See if you can figure out what would be the pressure at different points as water is flowing. So it'd be flowing kind of from left to right, for example. So water flowing under this valve, what's going to be happening with pressure? So you can see that now. Okay, so just press pause on that and we'll come back to it in a second. What we're gonna watch is, well, let's look at the solution for that first part right now. So what's gonna happen, does anybody wanna volunteer? What's gonna happen to the pressure as you go under the valve? Does it increase? What's gonna happen to the velocity as you go under the valve? Velocity has to do what? Increase. Why? Conservation of mass. So velocity goes up. What does that mean about kinetic energy? Where did that kinetic energy come from? If pressure goes up and kinetic energy goes up, we just violate conservation of energy. So if kinetic energy goes up, pressure has to go down. So as you go underneath that valve, I'm assuming most of you drew like pressure going up. And all of you are wrong, because it can't go up, because that energy has to come from, the energy for kinetic energy has to come from somewhere. So what I have drawn is something like this, and don't worry about the P saturated line yet. But what's going to happen is you're going to come in with some pressure. You'll lose that pressure and you'll trade off pressure for velocity. Pressure goes down, velocity goes up. Then when you go back to the left-hand side, so down here where your velocity is really high, your pressure has to be at its lowest. Then as you go back to the right-hand side, you go back to the full diameter of the pipe, velocity is going to go back down. So you're going to slow down. So you'll get some of your pressure back, but you'll lose some energy to friction. So you won't get all of your pressure back. Bernoulli's equation would say like your pressure will go down, velocity goes up, and then they go back, and you'd be back at the same total amount of energy. That's not what happens if you have friction losses. If you have friction, you don't get back to the same total amount of energy, you lose some. So this would be the head loss that you see. We're going to look at what happens when, say, this pressure down here gets really, really low. So if you go from high pressure, if you go to a high velocity, that pressure can actually drop. And it can drop so low that you go below the boiling point of or the saturation pressure of your liquid. So what happens is you don't go up in temperature, but your pressure gets down so low that you actually have boiling in this valve. It's an effect that we call cavitation. So we're going to watch this short video mainly because I like the music. But I think he does a good job describing cavitation.
Magnetic couple to the public surface is made of fluids. You can see the spinning tower inside. We can also see the fluid filter. It's got a gauge out here for discharge. It's got another valve over here on suction. And all the piping here is clear. So if you watch the flow of fluid. Right now it's all clear water, so we can't see much in that regard. It's got a rotator here showing us the amount of flow. What I'm going to demonstrate here is cavitation. We're going to purposely cause cavitation to occur in the system. We're going to do so by keeping the discharge valve wide open like it is and pinching off the suction valve. What that will do is reduce the pressure that's fine. And you'll see this compound gauge showing stronger and stronger backing as we begin to pinch off this valve. Let's start to turn this clockwise, and you'll see the gauge's indication go down. You'll also begin to hear cavitation take effect. We'll be able to see the bubbles form inside here as it cavitates after it vacuums the vapor and cavitates the liquid again here. So here we go, blows into that. And watch the gauge. Gauge will go down. -10 -12. 14, you can start your flashing through there. 16. More noise. -18. -20. You start to hear that sound. It sounds almost like rocks going into the pipe. There's no debris. There's no solid material in here. That solid sounding sound is really the collapsing of the vapor bubbles as they go back to the liquid form. You really hear it out. You see it coming out of here. Very pronounced noise. As the water goes to the valve.
I'm going to explain it and not let him explain it. So what's happening, the reason you hear that terrible sound, your pressure is going down, and it's going down so far that you boil and form a vapor bubble, like boiled water vapor. Then when you come back up here, your pressure goes back up. So you dip down below the saturation pressure, form a bubble, then you slow down and go back up in pressure, and that bubble collapses. That collapse is super fast because it happens really, really quickly because you get a very fast pressure change. So that can actually, that's what you're hearing, that huge like rumbling noise. You're hearing the collapse of those vapor bubbles. Just one more video. This one's kind of fun. This is a hydrofoil. So we've already looked at what happens with like wings in air. This is the same thing. This is a wing, but it's in water. And it's actually kind of more fun because it's in like basically a version of a wind tunnel, but it's with water. Which if you imagine like a wind tunnel has a big fan. So this has a big motor. It's like a 1,500 horsepower motor. It's huge. It's moving, when this thing's up to full speed, it's moving 20 tons of water per second. So this is kind of a wild piece of equipment, but it's used for looking at things like this. So they're going to be looking at this hydrofoil. You can see the water moving pretty fast, and they're going to be slowly increasing the velocity. So as we go to higher and higher velocities, we're going to be having bigger velocity changes and therefore bigger pressure changes. There, you start to see it right there. Right at that front leading edge where we get the lowest pressure. So that's a vapor bubble. It's boiled water. So you can continue to see the faster they go, the larger of a section of the hydrofoil is now in this cavitation bubble. So this is happening, I think they're getting up to like 18 meters per second, which is 40-ish miles per hour. So it's quite fast, but it's not like absurdly fast. So if you've ever been on or seen like the boats that are going to Lake Nakatawa, like the hydrofoil boats up Lake Nakatawa, does anybody know what I'm talking about? They'll have those. So those can go fast enough that you can actually have some of these effects on those hydrofoils. And you have to design then your hydrofoil knowing that it's going to be in cavitating conditions. Because cavitation, a lot of times, it can affect the performance of whatever piece of equipment that you have. But the other thing that it can do, it can be very damaging to equipment. So these are a couple of propellers and things that have experienced cavitation, and then a valve stem down here at the bottom left. And basically what happens, these bubbles, when they collapse again, it kind of like shoots out little water jets that can, especially metal surfaces that really have no give. Plastic does better, but metal surfaces can just be chewed up by this. So if you have propellers, if you have a pump that you're routinely experiencing cavitation in, it can end up in a very short order looking like this stuff here. So it's typically something that we're going to try to avoid in piping systems and plumbing systems. If it's something that you can't avoid, then it's something that you have to design knowing that it's going to happen. So we'll pick this in-class assignment. We'll pick it up next time on Friday. So just make sure you bring it with you when you come back Friday. Otherwise, have a great Wednesday.